This is going to be our second video on electrostatics. It's going to go through electric field, electric potential. We'll also get electric potential energy in there. We will reference that. So this is that second point here. I'm basically just going to talk about electric field and electric potential that's created from a point charge. I'm going to do some problems in class or possibly on a video where we're going to go through fields and potentials of other charge distributions. And so that's a lot of math and a lot of just kind of identifying these concepts with other charge distributions, such as cylinders and spheres and things like that. But right now we're just going to talk about the electric field and electric potential relating to a point charge itself. So the electric field is an abstract concept that is used to identify the force that a test charge would experience if it were placed at that point in an electric field. So the relationship between the electric field and force is that the electric field is the force divided by the test charge. It's an abstract concept of how big is that force per unit charge, not per unit distance, although there is a distance term in there. Because of that, here's Coulomb's law, and then there's the dr part, and the electric field is kq over r squared. Electric force, according to Coulomb's law, was kq1 q2 over r squared. So this is that force, again, without the test charge actually placed in there. It's a measure of what the test charge would experience, just based on the charge from the source. It is a vector, again, so the electric field is always going to point in the direction that a positive test charge would experience a force. So it's always going to point in the direction away from a positive source charge and toward a negative source charge. It says here a direction indicated that is the same as that of the electric field vector. The direction of the line is that a force on a positive charge would experience. So again, electric field lines will run away from a positive source charge and to a negative source charge. And they should actually be attached to that source charge if you're going to draw electric field lines. Also, the number of electric field lines should indicate the strength of the electric field in that region. And the electric field line should always be perpendicular to the surface of the source charge, or perpendicular to the source. So if you come down here, we've got electric field lines here, which are pointing away from the positive source charge. Each one of them is perpendicular to the source charge, and they actually originate here. Notice they are more concentrated here, and there are more of them in this region than out here because the electric field is stronger here. Here, same sort of diagram, except the electric field lines are pointing toward a negative source charge. All right, any questions about electric field there? You can sum electric fields. This would be two opposite charges. Notice how that happens. This is two of the same charges, and you get this asymptote, but it's still perpendicular to the source charges at the source itself. Here, we have a charge of positive 2q and negative 1q. So you should have double the number of electric field lines attached to this positive as you do to the negative, and we do. Okay, let's talk about voltage or electric potential. Oh, before I move on to that, the motion of a charged particle in an electric field, if you place a test charge in an electric field, it will experience an electric force. And we know that force is mass times acceleration. So in that case, that charge will accelerate based on its mass. Notice here we had an electron that came in with zero acceleration, but zero velocity in the y direction, but it experienced a force in the negative y direction because of this electric field, which was in the positive y direction, and that caused it to accelerate in the negative y direction, it still had an initial velocity in the x direction, which gave it this parabolic motion, very similar to the second half of projectile motion. Okay, there's electric field. Electric charges, y'all should be familiar with all this. I'll scroll through it, but this is also in your book. You can look it up as well. That should all be familiar. And then F is equal to QE. That's one you should probably commit to memory or understand really well. Oh, that's not what I meant to do. Let me do this. Let me go to a different. Let's go to electric potential. Oh. All right, electric potential, which is also called voltage, is going to be, it's sort of analogous to height from gravitational system, or analogous to pressure for a water system. The voltage is, again, sort of an abstract concept of what the electric potential energy would be if you placed a charge in that location. So here it is. The electric potential energy, which is a potential energy based on the distance that two objects are from each other. I'm going to come back to that in just 1 second. But if you don't want to define the actual electric potential energy, but instead how much energy an object would have if it were placed at a certain point, that is called the voltage, or the electric potential. So let's go back to electric potential energy. We've said that gravitational potential energy, or elastic potential energy, or any form of potential energy is related to the stretching or compressing of a system. With gravitational potential energy, it was the system with the earth and a ball. With elastic potential energy, it was the two ends of a spring. With electric potential energy, it's related to how close or how far apart two charged particles are. If they are closer together, they will have less potential energy, and if they are farther apart, they will have more potential energy, which seems kind of backwards, but it is the way it works, just like gravitational potential energy. And things always want to move to the point of lowest potential energy. Let's see where I want to go with this. EDS. Work is still going to be the negative change of potential energy. That has not changed for mechanics at all. Yep. And we know that the force, like work is force times distance. So the electric force is QE. So that's where we're getting negative QE ds, which is where we're getting this. The ones I use for the most part, I believe this is all on your formula sheet. Y'all should check. But I want you to understand that potential energy and work have a negative relationship there, and that voltage is that abstract concept of the potential energy without placing a test charge, without putting that second half of the potential energy in there. So if you remember, I said you can't have a gravitational potential energy unless the Earth is part of your system. You could still have a height above the ground. Well, this is sort of the same thing. You can't have an elastic potential energy without placing two charges, a test charge and a source charge. Without the test charge there, you can define the voltage, which is kind of an abstract concept of how much potential energy a test charge would have in that location. You do need to know this one, that potential energy is equal to negative Q delta V, or that work is equal to positive Q delta V, either one, but that one is so if you take a charge and you move it through some potential difference, work will be done to move a charge through some potential difference. Let's see if I can find a diagram for that for y'all. So here we have an electric field, and we have a potential at point A, and we have a potential at point B. And if I'm going to move my charge from point A to point B, then there will be work done on that charge. And here's the relationship. Again, the change of potential energy is Q delta V, which is negative QED, which is negative, like the change of voltage is the negative change of electric field times distance. So if you move a charge through an electric field some distance, then that gives you its change of voltage there. Or in other words, electric field is a measurement of the rate of change of potential. Electric field is a measurement of the rate of change of potential. But you will have more potential if you are, I get this right, you have more potential if you are farther from a positive source charge. And you will have less potential if you are closer to a positive source charge. This is going through changes of potential energy again. If the electric field is a measure of the rate of change of the electric potential with respect to distance. So this is the definition of voltage in relation to just our basic variables, K, Q over R. Potential is not a vector. It is a scalar. Again, here's that relationship between voltage and electric field. Electric field is a measure of the rate of change of voltage, but they are in opposite directions. So let's do this one. Quiz. In a certain region of space, the electric potential is 0 everywhere along the x-axis. From this information, you can conclude that the x component of the electric field in this region is, and in that case, the electric potential, remember the electric potential is the voltage, which is the rate of change of the electric field. So this should be 0. It is. Suppose that it's positive 2 everywhere along the x-axis. From the same choices, what can you conclude about the x component of the electric field now? Well, since it is positive 2 everywhere, it is not changing. It doesn't matter what the electric field's value is, or what the electric potential is, what the potential is, what the voltage is. If it is not changing, then the electric field is 0. So this should be 0 as well. It's the rate of change of potential would give you the electric field. Again, this is the definition in terms of our basic variables. V is equal to K dQ over R. And we will do some math with those. I recommend y'all run through and kind of look at these examples here, but I'll also probably go through them with you in class or make another video with just those math examples. And we will get to conductors in just a minute after we go through Gauss's law. So this is the end of the second video. Let me know if it was too confusing. I will go over that material in class again if you need me to. Edit. How do I stop it? We're working on it.